Advanced Photonics.
As a Joint Chief Editor, I would like to take this opportunity as AP's 5-year anniversary to express my gratitude to the remarkable journey that we have taken together with our authors, readers, reviewers, the editorial board, and the publishers, the Chinese Laser Press and SPIE.
这个期刊自创刊以来，得到了广大的国内外的这个科研人员、学生和科研工作者的高度的重视和积极的参与，成为我们光学领域里面一本有重要影响力的期刊。
I would like to invite you to publish your best results in Advanced Photonics and Advanced Photonics Nexus. Over the last 4 years, these journals have become among the top in the photonics field of research.
We really welcome your contributions in all aspects of photonics. So if you have some exciting new research that you would like to get into a high-impact journal, because our impact factors are right now extremely high, we really welcome your contribution.
The hard work we've been doing for the last several years on using plasmonics for doing photochemistry.
I got interested in atomic physics when I was a student at Ecole Normale.
Very good work to the top journals, and I now consider Advanced Photonics to be one of the top journals.
We cover a wide range of optics technologies, ranging from microscopy through to laser-based manufacturing.
Happy birthday to Advanced Photonics. I think the work that you and your editors have been putting together since 2019 is really inspirational, and wish you all the best in the next 5 years and the next 5 years of success. Thank you.
也能跟大家交流一下我们在那个宽视场超表面光学方面做的一些工作。
What you see on this optical table is our custom photoresolve microscope.
是既是一个新的一个课题，那么也是一个老的研究方向，已经研究了几十年，我们这个领域发展所面临的机遇。
Advanced Photonics is made by scientists, for scientists, and we are very eager to hear from you how we can improve it and how we can develop it further. Please submit your best research to Advanced Photonics.
Happy birthday, Advanced Photonics!
As a Joint Chief Editor, I would like to take this opportunity as AP's 5-year anniversary to express my gratitude to the remarkable journey that we have taken together with our authors, readers, reviewers, the editorial board, and the publishers, the Chinese Laser Press and SPIE.
这个期刊自创刊以来，得到了广大的国内外的这个科研人员、学生和科研工作者的高度的重视和积极的参与，成为我们光学领域里面一本有重要影响力的期刊。
I would like to invite you to publish your best results in Advanced Photonics and Advanced Photonics Nexus. Over the last 4 years, these journals have become among the top in the photonics field of research.
We really welcome your contributions in all aspects of photonics. So if you have some exciting new research that you would like to get into a high-impact journal, because our impact factors are right now extremely high, we really welcome your contribution.
The hard work we've been doing for the last several years on using plasmonics for doing photochemistry.
I got interested in atomic physics when I was a student at École Normale.
Very good work to the top journals, and I now consider Advanced Photonics to be one of the top journals.
We cover a wide range of optics technologies, ranging from microscopy through to laser-based manufacturing.
Happy birthday to Advanced Photonics. I think the work that you and your editors have been putting together since 2019 is really inspirational, and wish you all the best in the next 5 years and the next 5 years of success. Thank you.
也能跟大家交流一下我们在那个宽视场超表面光学方面做的一些工作。
What you see on this optical table is our custom photoresolve microscope.
既是一个新的一个课题，那么也是一个老的研究方向，已经研究了几十年。我们这个领域发展所面临的机遇。
Advanced Photonics is made by scientists, for scientists, and they are very eager to hear from you how we can improve it and how we can develop it further.
不好意思啊，我们再等一下这个 Lvovsky 教授，因为上一次我们那个开始的时候开始就比较准时的就到了，我们稍微再等一下。
As a Joint Chief Editor, I would like to take this opportunity as AP's 5-year anniversary to express my gratitude to the remarkable journey that we have taken together with our authors, readers, reviewers, the editorial board, and the publishers, the Chinese Laser Press and SPIE.
这个期刊自创刊以来，得到了广大的国内外的这个科研人员、学生和科研工作者的高度的重视和积极的参与，成为我们光学领域里面一本有重要影响力的期刊。
I would like to invite you to publish your best results in Advanced Photonics and Advanced Photonics Nexus. Over the last 4 years, these journals have become among the top in the photonics field of research.
We really welcome your contributions in all aspects of photonics. So if you have some exciting new research that you would like to get into a high impact journal, because our impact factors are right now extremely high, we really welcome your contribution.
And Professor Guo Haisitu will be the host.
The hard work we've been doing for the last several years on using plasmonics for doing photochemistry.
Or I was interested in atomic physics when I was a student.
According to the schedule, I need to the top journals, and I now consider a very short introduction to one of the top journals.
Advanced Photonics range of optics technologies, ranging from microscopy through to laser-based manufacturing.
Happy birthday to Advanced Photonics. I think the work that you and your editors have been putting together since 2019 is really inspirational, and wish you all the best in the next 5 years and the next 5 years of success. Thank you.
也能跟大家交流一下我们在那个宽视场超表面光学方面做的一些工作。
What you see on this optical table is our custom photoresolve microscope.
既是一个新的一个课题，那么也是一个老的研究方向，已经研究了几十年。我们这个领域发展所面临的机遇。
Advanced Photonics is made by laser technology.
I'm great to be the host for today's live stream for Advanced Photonics and Advanced Photonics Nexus. So first, let me introduce these two journals at the beginning. Advanced Photonics was launched in 2019, and 2 years later, it was indexed in SCI Extendix version. And in 2022, Advanced Photonics got the first impact factor, which is 13.6. And we also launched the sister journal, AP Nexus. And now, for this year, The AP impact factor is something like 18.8, and AP Nexus also got the first impact factor, 6. The journal have 2 editors, which is led by Larry Yuan and also Professor Anthony from King College London, and also Professor Weibel Chen from Shanghai Institute of Optics and Fine Mechanics. So we try to do a very rapid publication. The time to publication is something like the median day is 18 days. So you see from this figure here, the first round reviews, it takes something like 40 days. We will try to make the first review by the editor member in 3 days, and in 10 days we send the papers out for review, and we hope you get the first review back in a month or so. So after the review process, the production will take something like 20 days if the paper is accepted. And in altogether, it's something like in 3 months or so, the paper, if you're lucky enough, you get your paper published. So here in this slide, we show some very good paper have been published in the Advanced Photonics and Advanced Photonic Nexus. So you will see that some of the good paper have been cited or highlighted by very decent journals, such as Nature and Nature Photonics. And we also have a very specific arrangement for papers, which has been submitted and reviewed in some decent journals, such as Science and Nature's journals. So here we highlighted 4 of the examples, which had been submitted to Science, Nature, Machine Intelligence, or Physical Review Letters, and Nature Communications. So in this case, the editor members will get a very quick precision to the papers which had been submitted to these journals, and if you have also submitted the review report at the same time. So besides this journal publication, we also publish interviews to some leading professors in the field of photonics. In the past few years, we have interviewed with some very famous optical scientists, such as John Pendry and Shining Zhu and Yuri Grisas, and also something like that. And also we had SPIE and COP conference on advanced photonics, which is launched the first time in 2022, which is, you may know that this is also the pandemic in China. And in the first year was held in Hangzhou, which is a very beautiful city in China. And in 2023, we have the conference held in the United States, in San Diego. And you see the list of invited speakers, which is very quite outstanding professors here in this field. And this year, the conference will be held in Hong Kong, which is organized by Hong Kong Polytechnic University. And we have 4 very famous plenary talkers, and we have 4 very specific and hot topics nowadays in the field of photonics, such as AI photonics, laser and nonlinear optics, and nano photonics and quantum optics, and sensing and imaging. So besides this, we also have multiple platforms to promote the papers published in Advanced Photonics and AP Nexus. For example, we have Twitter and WeChat articles. Now we have more than 4,000 reads in the scientific media and social platforms. And we have also more than 100,000 views for video presentation. And also for this live streaming, which has been attracted more than 30,000 online viewers. So today we are in the live stream time. We have this is very honored to have the Professor Alexander Lvovsky from University of Oxford, who will talk about his recent paper published in Advanced Photonics. The title is Training Neural Networks with End-to-End Optical Backpropagation. So let me first introduce Professor Alexander Lvovsky first. So he's a professor at the University of Oxford, where he conducts wide-profile research on quantum and optical technology. Alex is a part candidate, Canadian Research Chair, a Fellow of American Physical Society, and a Fellow of Optica. His accolades include the International Quantum Communications Award, commendation letter from the Prime Minister of Canada, and the $1 million Research Award of the German Science Foundation. His work has been featured by CBC, NBC, Wired, New Scientist, MIT Technology Reviews, and The Guardian, and even Daily Mail. So now the platform is yours, Alex. So I close my share screen. Okay. So
thank you.
Welcome, Alex.
Thank you for the nice introduction, and also it's great to hear about Advanced Photonics. I mean, I love your journal, but now I'm even more eager to publish in it. So
I hope you will publish more paper on these journals.
Let me share the screen. Let's see. Do you see my window, right?
Yes.
Okay.
Yes, and sorry, Professor Lvovsky, could you maybe be more closer to the mic so everyone can hear more clearly?
Yes. How about now?
Okay. Yeah, much better.
Yeah. Do you see my full screen?
Yes, we can see.
Okay. Excellent. Okay. Then let's proceed. So thank you very much for inviting me. I'm going to present two topics, one on computer vision and one on using optical neural network for optimization. I guess I don't need to tell you nowadays that machine learning is taking over, the artificial intelligence is taking over the world. I'd like to make the statement that nowadays machines perform better than humans in all worlds that they have complete information about the environment. So they can drive cars, they can calculate integrals, they can recognize faces, they can play chess. So the only environment in which they do not yet rival humans is our everyday environment. So robots are not yet on par with humans, but everything else is. So it's kind of the final frontier. But the point I want to make now is that AI is powered by neural networks, and we are facing a challenge in developing neural networks. Namely, if we look at the demand for computational hardware in the past years, we see that for a very long time it's been exponential, which is not surprising. But what is somewhat surprising is that if we just focus on the past 10 years, we'll see that the coefficient of this exponent has increased. Has increased and significantly outpaces the development of computational hardware. So the demand has grown in the past 10 years, and when I talk about 10 years, it's the time interval from first convolutional or like somewhat advanced convolutional neural networks to modern LLMs. So the demand in compute has grown by 6 orders of magnitude. At the same time, the supply has only increased by about 1.5 orders of magnitude. So there's a significant gap, and in fact, it's kind of unsustainable because already now 4% of the world's electric energy is now used by data centers. This number is growing exponentially. By 2013, we expect this number to become 13%. So this trend is clearly unsustainable. And what can we do about it? Well, to answer this question, we should compare digital computers with the brain. And if we do make this comparison, that we see that in terms of speed, in terms of operations per second, the two systems are quite similar. Well, 10 power 15 operations per second is the productivity of modern GPU, and it's comparable to that of the brain. But in terms of energy efficiency, in terms of operations per joule, the performance is significantly poorer. Right here, with a digital computer, we have 10 power 12 operations per joule, and with the neuron, it's some 10 power 15 operations per joule. Now, why is it? It's actually quite easy to explain, because in a neural network, the costliest operation is matrix vector multiplication. Right? So, well, basically multiplication. If we just multiply two 32-bit numbers, it's 1,000 single-bit operations, each of which is a non-trivial physical process. And we have trillions of these operations in a digital neural network. In the brain, on the other hand, we have analog computing. That is, each neuron routinely implements scalar multiplication of two vectors. One of the vectors arrives via the dendrites, the other is stored in the body of the neuron. The two vectors get multiplied, they produce an activation pulse, which then propagates via the axon. So because it's analog, it's much less expensive. And then the question that, the next question we should ask is there a technologically accessible platform that can operate more like the brain and less like a digital computer? And once we ask this question, the immediate answer that we get is optics, because the light wave, as it propagates, it experiences interference and diffraction, which can in fact realize an arbitrary linear operation. I'll show you in a moment how it works. The point I want to make now is that the optical computing, at least in theory, can surpass digital machines and moreover surpass the brain, both in terms of productivity and in terms of energy efficiency. Well, okay, so before I continue, I'd like to give you a first kind of a very brief introduction of how neural networks work. So suppose we have a task of recognizing an object, that is, we want to distinguish a cat from a dog. The input is a bitmap. Well, it's a bitmap, but mathematically we treat it as a vector. And then our task is to calculate the function of this vector, which is the probability of being a cat or a dog. Obviously, our brain is quite good at calculating this answer, but how can we get the machine to calculate it? Well, we create a structure like this. We take an input vector and multiply it by a matrix, which we call the weight matrix. And then we, to the output vector, we apply the so-called activation function, some nonlinear function, which we don't train. So this weight matrix we optimize, and which we call training, but then the activation function is fixed, right? And then we apply multiple layers to repeat this process many times. Like this. That's why it's called deep neural network. And there is a theorem which says that any function, however complicated, can be approximated by such a structure, provided that we have enough layers and enough dimensioning of this layer. So if we try to implement this optically, well, there are kind of, to give you an overview of technology, there are two main avenues along which this technology has been developing. One is free space on optical tables, and the other one is integrated on the chips. On the optical table, the information is encoded in the spatial structure of light, and spatial light modulators are used for store weight matrices, and for the integrated setting, the information passes in waveguides and waveguide interferometers are used for weight matrices. Now, obviously, this column on the right is much more appealing, right? Because you can make it at the factory. You don't need to align it. You can just ship it to the customer. This looks much bulkier and clumsier. However, the integrated setting has a problem at the moment, namely the scalability. You see, if we want to multiply a vector of size 100 by a matrix of size 100 by 100, the matrix needs to, there needs to be 10,000 beam splitters here on this chip. And each of these beam splitters must be controllable, so there must be a wire connected to it. So we must have 10,000 wires connected to our chip. And that limits the size, limits the scalability. In free space, on the other hand, we have spatial light modulators. A spatial light modulator, well, it's basically like your computer screen. It can easily have the size, the resolution of megapixels or even tens of megapixels. So at the moment, the free space technology is much more scalable than the integrated technology. Now let's make a simple estimate of how, I quoted these numbers previously. I want to show you how I arrive at these numbers. So in terms of productivity, it's quite easy. Suppose I have a matrix of the size 1000. When I do matrix vector multiplication, it's 1,000,000 operations. And then I need to multiply this number by the rate at which the data is applied to the neural network. Assuming that we use electro-optical modulators, these modulators can easily have a bandwidth of 10 or even 100 gigahertz, right? So conservatively assuming 10 power 10, multiply these two numbers, I get 10 power 16 operations per second. In terms of energy efficiency, it's somewhat more complicated. Basically, what we say is that, well, for each of these 1,000 outputs of a matrix vector multiplier, we need a reasonable number of photons to overcome the shot noise. So, for example, if we have 10,000 photons, the shot noise is the square root of that, which is 1%. So 1% is something we can live with. Assuming that we have 10 power 4 photons in each output, we'll have only 10 photons per operation. Right? So, yeah, so remember that we have 1,000 outputs, but 1,000,000 operations. So we need to divide this number by 1,000. And in fact, there were papers where they've shown that one can have even less than 1 photon per operation. But in any case, in this simple calculation, it's 10 photons per operation, which is 10 power minus 17, 10 power minus 18 of a joule. Now, let's compare it with the modern, with the most recent NVIDIA machine. It's like, the most recent consumer video card. And what you see here is that the productivity is some 10 power 15 operations per second. So it's comparable to what we have with optics. But in terms of operations per joule, it's some 10 power 12. So it's much, much less efficient energetically. One caveat I have to make here is to say that, I quoted here 10 power minus 17. Well, this benchmark increases significantly by 3 orders of magnitude if you need to convert between digital and analog format of data. So if you want to use an optical neural network to process data, you better already have it in some kind of optical form, or at least to not interconvert between digital and analog formats during the processing. Now, this slide shows the principle how an optical matrix vector multiplier works. So what you see here is a vector, right, which is represented by an array of lasers of different intensities. And this is the matrix, which is, as I said, the spatial light modulator, transmissive spatial light modulator. And what I do is I spread my vector element over the row of matrix elements. Then as light propagates through the matrix element, multiplication occurs, right? Because the transmitted light is a product of the incoming light times the transmissivity. And then I focus the vertical dimension onto a slit here, which kind of adds together the contributions from all rows. So as a result, I get summation. And so in practice, this is so this has been done. We are not saying that we were the first ones. In fact, the idea has been around since more than 40 years. But at some point, we were the largest. So we can do matrix sizes of a few hundred. And in fact, I have the startup company Lumai, which specializes in streamlining these matrix vector multipliers, making them fast and high dimension. Now, here are some examples of what have been achieved with this technology. Here's a paper from some 2 years ago, here from McMahon's group at Cornell. So here they made a computer vision system that is able to, that's a 2-layer optical neural network with an analog activation function, and they were able to read the message of the road sign, like a speed limit sign that's 3D printed. Here's a more recent example. Here they construct what they call meta surface. There's just one layer is optical. This optical meta surface that converts visual data, and then there is a digital head here, but the digital head has much fewer operations than the optical part of the neural network. And with this neural network, they are able to surpass AlexNet in recognizing visual images like those shown in the picture. Here's one example from China. Professor Lu Fang. So here, if previous examples here were free space optics, this is integrated optics. And as I told you, integrated optics is difficult to scale. So here, their linear process, their integrated processor is only of size 8 by 8, right? And it's preceded and followed by a reservoir, so by a random layer which increases the dimension. And they had 20 such chips constructed that simulate about 10,000 chips. And with this machine, they are able to reach the operational speed of about 160 tera operations per second, so 10 power 14 operations per second, and they can do a large variety of complex computational tasks, such as recognizing images or painting in Van Gogh style, or writing music in the style of Bach. So here I should emphasize that, in fact, not the whole thing is digital, like all the matrix vector multiplications are done digitally, but in fact, there was a digital computer heavily involved. 20 chips were emulating 10,000, a machine with 10,000 chips. Good, but the focus of what I want to talk about today is on training. So let me explain training. So what is training? Training means finding the weight matrices. I've shown you the structure before, and the weight matrices are optimizable. So we want to optimize the weight matrices so the neural network performs the task that we need. To train the neural network, we need a so-called training set. That is multiple examples of cats and dogs, including correct answers. So for each example, we need a correct answer, whether it's a cat and a dog. And once we have that, then we can calculate the so-called loss function. That is the difference between the neural network output and the correct answer, squared and summed for all outputs. The good thing about the loss function is that it's differentiable with respect to the weight matrices. That is, we can calculate the gradient of the loss function with respect to the weight matrix and then apply gradient descent. Yeah, so once we have the gradient, we can iteratively optimize the weight matrix to minimize this loss function. Now, on the next slide, I have to, to explain my work, I have to go a bit further into detail how this gradient works. In fact, the gradient can be, there is a simple equation for the gradient. So the gradient of the loss function with respect to the weight matrix, with respect to a particular weight matrix in layer L, or it's a matrix which is an outer product of two vectors. the first vector is the input vector of neurons coming in, and the second one is a so-called error vector. What's this error vector? Well, the error vector in the very last layer is the difference between the neural network output and the correct answer, the label. Then what we do for previous layers, we take the error vector in the next layer, multiply it by the derivative of the activation function, and then multiply by the weight matrix. That gives me the error vector in the previous layer, and then I go backwards, starting from the last layer, go all the way to the first layer. This is the so-called backpropagation algorithm co-invented by Hinton back in 1986, which basically jump-started the field of machine intelligence. Now, how can we train an optical neural network? Well, to be honest, in most cases, including those cases I showed you previously, the training is done by means of a digital twin. That is, people build a simulation, and a digital simulation of an optical neural network, train that simulation, and then apply whatever matrix elements, weight matrix elements they've calculated to their SLM. Obviously, this approach has shortcomings. Well, first of all, you need a digital twin, and of course, what's the point of making an optical neural network if you still need a digital twin? And second, you are sensitive to errors because no simulation can be perfect, and therefore there'll be errors associated with this imperfection. A partial solution to the second problem here is so-called hybrid or physics-aware training, in which, well, as I said, for the gradient, you need both the activation values and the error values. And the idea is to calculate the error activation values using the optical neural network, and then to calculate the error values using the digital twin. So you still need a digital twin, but because you have physics in the loop of training now, the sensitivity to errors greatly reduces. So it solves the problem partially, but then the big question that I want to ask, can we also calculate the error? Can we also backpropagate optically? And the answer is, well, if we look at the forward propagation and backward propagation, we see that the structures are quite similar. In fact, the linear parts are very similar. So if we just backpropagate light through the same interferometer, but backwards, it will do the linear part of the backpropagation operation. So you see, the term backpropagation was initially like a mathematical abstraction. And the question that we are asking here is, can we implement backpropagation actually by physically backpropagating light through our optical neural network? And the answer is that for the linear part, it looks very good. It's quite possible. It's exactly the operation we need. But for the activation function, it's a problem because you see in the forward direction, the activation function is nonlinear. But in the backward propagation, it has to be linear. We have to multiply by a certain number, by the derivative of the activation function. And as we know, there are not many optical elements that exhibit different properties for forward and backward propagation, right? So we have these three requirements, right? We must have an activation function that's nonlinear for forward propagation, linear for backward propagation. And when we say linear, we actually mean multiplication by a particular number, the derivative of the activation function. So can this be solved? The answer is, well, the answer is as follows. 1 and 2, well, they look difficult, but actually they are not difficult because it's quite well known that nonlinear optics is strong for strong light, but weak for weak light. So if we make forward signal strong, but backward signal weak, we actually can satisfy both conditions 1 and 2. But for condition number 3, it's more difficult. So basically what we have to do is we have to search through a whole bunch, through a variety of nonlinear optical phenomena, and see if any of them happen to satisfy number 3, at least approximately. And luckily, we have been able to find, so colleague Xianxin Gu, who is now the CEO of Lumai, has been able to find such a phenomenon, namely saturable absorption. And indeed, if we take a saturable absorber, well, that's what the activation function looks like. And if we take the derivative, well, it's the red curve here. But if we actually calculate the backpropagation through a saturable absorber, it's an orange curve here. You see the curves match each other quite well for low intensities, and this is what we care about. There are some discrepancies for high intensities, but you see not many neurons take high values. Most of the neurons take low value, and therefore it's acceptable. And well, we built this apparatus to demonstrate that the idea works, and this was published in Advanced Photonics in this year. So here it's a relatively simple optical neural network with just 3 outputs, a single activation, single hidden layer with dimension 5, and 2 outputs. And then we tap off the neuron values after the first layer. So these are our activation values, and we then backpropagate the error backwards to the same neural network. We tap off the error vector after the after propagation through the activation cell, and this is then we get the error vector, and then we take the outer product between the neuron vector and the error vector here and here, and this gives us gradients for our 2 weight matrices. And here's an example of how it works. So the task we solve here is quite simple. It's classification of 2-dimensional points, right? So here we have the training set consists of 2 classes, the blue class and the orange class, and then we give our neural network a pair of coordinates x and y, and we ask it, does it belong to the blue class or the orange class? And as you can see, our optically trained neural network always gives a correct answer to this question. So it always identifies class correctly. So the background in this picture is the answer that the neural network gives for an arbitrary x and y. We always get the correct answer, in contrast to training with a digital twin, which is only 95% correct. So that concludes the first part of the talk. Now I'd like to also mention and a particularly important, I believe it's particularly important application of optical neural networks, namely the application for computer vision. So, well, to remind you what is computer vision, at least today, is we have some kind of object. We take a digital image of that object and then process the digital data with a digital neural network and acquire the information that we want. Now, importantly, many computer vision applications involve low light conditions. Think of a self-driving car that's trying to recognize an object like a pedestrian in a dark street or read a road sign, or we're looking at the star and we're trying to see if there is a planet around the star, or we're looking in a microscope at a virus, but the virus, like the biological sample, is prone to photobleaching or phototoxicity, so we cannot illuminate it for a long time. So again, we have limited number of photons. So a common feature of all these, there are 2 common features of all these examples. First, as I said, there is limited amount of light, but also second is that we don't really care about the image. We care about a particular feature of our object, such as the message of the road sign, or a type of virus, or the coordinate of the exoplanet. In all these cases, right, we don't care about the image, and because the number of photons is small, it is unwise to spend this limited number of photons to generate the image. So, yeah, so our goal is to extract some particular parameters of our object. And under these circumstances, it is beneficial to do something something new. Namely, before you detect light, you pre-process that light with an optical neural network, and only then detect it, convert it to digital data, and then process it again with a digital neural network. So now you have two neural networks, optical and digital, and you train them in concert in application to a particular type of knowledge, particular features of the object that you want to learn about. Right? So now, so importantly, when you set this task and when your light is weak, then you want to, when you train your optical neural network, you need to take quantum nature of light into account. So in that sense, it's not just an optical machine learning task, but a quantum optical machine learning task. And the good news is that, well, when the number of quanta is limited, for a given object, one can actually calculate how well an optical neural network can perform in principles. So there are so-called quantum criteria, quantum Fisher information for regression, and quantum Hellstrom bound for classification. So once you've trained your optical neural network, you can see if you did a good job by comparing the performance of your actual neural network with these quantum limits. So, okay, so let me give you an example, and I have to start from afar. Resolution, imaging resolution. Well, as you know from studying optics, when we have an imaging device, the resolution is limited by the diffraction on the objective lens. That is, if we're trying to image a point, the image will not be a point, but a blur. That's called the point spread function. And if the 2 points are close to, each other, then these 2 point spread functions will coalesce, and you won't be able to resolve the 2 points. You won't be able to measure the distance between them, and you won't even be able sometimes to tell whether it's a single object or two separate objects. And for the last few decades, like a number of ideas have appeared on how to overcome the diffraction limit. They can be divided into these three large families that are depicted here. One is near field microscopy, when we have some kind of needle near field probe scanning over the sample, so there is no objective lens and therefore no diffraction. Or there are nonlinear methods based on nonlinear optics, in which you get fluorescent emitters in your sample to light up one by one, and then every time you get just a sparse sample with a small number of emitters, which are easy to localize. And finally, there are methods based on non-classical light, such as squeezing entanglement or single photons. A common disadvantage of all these methods is that they all require some kind of active interaction with the sample. And that, of course, greatly reduces the applicability of these methods, right? Because even in microscopy, there are fragile objects that cannot be near field scanned, or there are objects without required nonlinear optical properties. But outside microscopy, right, there is astronomy or satellite imaging or remote sensing, in which you have no possibility whatsoever to actively interact with the sample. So it would be much nicer if we could improve the resolution passively by not actively interacting with the object, but simply analyzing the light coming from that object passively in a wiser way, right? And improve the resolution just by this passive analysis. But can this be done? Well, the answer was for a long time believed to be negative, because Abe and Raleigh are very smart people, their science was solid. But then Man-Kei Tsang came up with this idea of treating imaging resolution by a quantum sensing problem. That is, again, by constructing the optics that can find the optimal measurement of the incoming photons to extract the parameters of interest. So specifically what he proposed is to take the light in the image plane, and instead of measuring it directly, decompose it into certain basis of transverse modes, measure each mode, and then use this information to obtain the information about the object. It turns out that this reconstruction will have high information about what's obtainable via direct imaging. So here's a picture that that kind of gives you an intuition of this idea. So suppose we use Hermite-Gaussian basis and we filter Hermite-Gaussian mode 1, 0. Now you know that Hermite-Gaussian mode 1, 0 is an anti-symmetric mode which consists of two bulbs here, one positive, one negative. So suppose we have some kind of object, for example, a star on the optical axis of our apparatus, and we set a filter that only transmits the first Hermite-Gaussian mode. Well, the optical field here is symmetric, but the mode, our filtering mode, is anti-symmetric. So we'll have no light photon detector. Now, if the star is not on the optical axis, but slightly off the optical axis, then we'll have some light here, because the image here is now not completely symmetric. It has an anti-symmetric component which will be transmitted through this filter. If there are two stars, well, they are incoherent, so their intensities will add, and we'll still have some signal here in spite of even if the two stars are within the Rayleigh limit of each other, so even if they are not resolvable by standard methods, we'll still see some light here, and we can tell that there are two stars and measure the distance between them, and this measurement can be much more precise. So here, this picture summarizes the idea that you see by, well, we need to distinguish between a single emitter or two emitters. Well, if it's direct imaging, then we have to distinguish between a picture and a slightly different picture, which is difficult. By this new method, we have to distinguish between some light, between no light and a little light. Obviously, the second, the task in the second column is much easier than the task in the first column. So here's an example of how optical pre-processing allows you to solve certain tasks much more efficiently than direct imaging. Now, our contribution to this, so since the discovery of Monkey, there's been a lot of groups have jumped onto it and done a lot of work. Our contribution to this field has been to do proper imaging, so to not just to measure some parameters of the object, but to actually image the object. And well, here I'll show you some results. So here we imaged the logo of our university. So on the left column is the actual logo. In the middle column is direct image of that logo. So here we artificially impose the diffraction limit by setting a narrow aperture in the light path. So because of diffraction, the image gets blurred. But then with the same aperture, with the same diffractive limit, would apply our new method, this Hermite-Gaussian processing, and then the quality of image greatly improves. The resolution enhances by a factor of 2 or 4. So far we've done it with a number of settings: coherent light, incoherent light, and also we've done confocal illumination, which enhances resolution at the illumination point in addition to the detection point. So these pictures are not yet with a proper microscope, but recently we've started venturing into microscopy, and then we also see significant advantage. For example, well, here you can see, well, this is a so-called fluorescent target. This number 4,000 means 4,000 lines per millimeter, or 4 lines per micron. So it means that the distance between lines here is only 250 nanometers. With direct imaging, you can barely resolve them. But with our new method, you can resolve them. You can resolve them much better. So you see the gap between the lines is even half the size, like 125 nanometers, and you can still see this gap very clearly. As an added bonus, like you've all used microscopes, you know that if you move the microscope objective up and down, you will defocus your image, right? So your image will look something like this. But turns out that with our new method, it's no longer the case. You can, you still get a sharp picture. Yeah. So to conclude this part, right, we've developed a method of passive linear optical we developed a method that overcomes the diffraction resolution limit in the regime of passive linear optical and far field imaging. And we've tested it in a variety of microscopy modalities, and we've well, now we're starting to validate it in a true microscopic setting. So here's a kind of a market picture what we hope to achieve. So the horizontal axis is the resolution, and the vertical axis is the cost. And you see these two gray clouds are existing methods, right? So on the one hand, there are these diffraction limited methods. On the other hand, there are those other methods, super resolution methods that I mentioned in the beginning that are limited to specific samples. Our technique is somewhere here, so it gives you another half an order of magnitude in terms of resolution. But in addition, it also but it's not limited to specific samples, it's universal, and it's reasonably priced because all you need is bespoke optics. Now, how is this whole thing connected to optical neural networks? Well, you see the smooth sorter here that sorts, that measures in the transverse basis is actually an optical neural network, right? So the way it's implemented is you have a spatial light modulator from which light bounces back and forth to send each transverse mode in its own separate spatial direction. And so what we can do is we can train this we can train the spatial light modulator to achieve tasks that we need. So here I'll skip a couple of slides because to save time, but I want to show you this. I want to show you this slide here, which is our recent work, not yet published. Here we are looking at discriminating fashion MNIST. That is, well, you might have heard of fashion MNIST. It's like MNIST, but instead of 10 classes of handwritten digits, here we have 10 classes of fashion industry images. So like t-shirts, trousers, sneakers, bags, and so on. And the task of a neural network is to distinguish them. Now, the task that we set is we try to distinguish classes just based on a single photon. So you see, we have just one photon from an object, and we're trying to tell, for example, is it t-shirt or is it a pair of trousers? So this table here shows the accuracy of distinguishing between each pair of classes. So for example, this class 0 is t-shirts, class 1 is trousers, this number 58 shows that if we just have one photon, from an object, then we can distinguish these classes with 58% accuracy. The baseline being 50%, right? So if we just randomly guess, it's 50%. With direct imaging, we can distinguish slightly better with 58% accuracy. But now, if we construct an optical neural network, we can do much better. We can distinguish with 73% accuracy, which actually approaches the quantum limit. So quantum limit here is 77% accuracy. So our optical neural network in application to computer imaging surpasses direct imaging and approaches the ultimate quantum limit. So to summarize, right, optical neural network, well, I say rival to quantum computing. Of course, fundamentally, it's still a classical computer, but the good news is that it can significantly surpass the capabilities of a digital machine with the technology that is already available. So unlike quantum computing, it's not science fiction, it's something that's already there, already. All the technologies has been developed, and we just need to put these components together. And the particular contribution that we've made is that we can train optical neural networks by actual physical backpropagation of light. And then I showed you a particularly attractive, in my opinion, application of an optical neural network for machine vision. right, for quantum computational machine vision, and I've shown you applications in super resolution imaging, but also application for object classification. You see, okay, the last point I want to make is that, of course, we all know about this race to develop a quantum computer. We know how difficult it is to develop a quantum computer that would have advantage with respect to a classical machine. All existing examples are controversial. There is no proof now. But when we talk about computer vision, when our input information is not digital, but it's already available in the form of light, then quantum advantage is actually not difficult to achieve. And it's natural to use an quantum optical neural network to process your light optically, so it preserves the quantum properties of light, and then it gives you advantage. So you can really have, so that would probably be the first example of quantum advantage, of advantage of quantum computation compared to direct digital computation. Thank you for listening. Hello.
All right. Thank you, Alex. It's a wonderful talk on optical neural network and also for quantum imaging. So now we have time for a few of questions. Yeah, so are there any questions from the audience? Well, I got the first questions. Is related to this. So Alex, so the question is it possible for the scanning Gaussian imaging surpass the R-based limit while the illumination is band limited?
Yeah, well, band limited, you mean you mean the spectrum, right?
Right, I think so, yeah.
Yeah, all experiments are monochromatic, but of course, actually, if the light is not monochromatic, it creates complications because these diffractive neural networks, they are wavelength sensitive. However, there are methods to overcome this issue and make the diffractive neural network insensitive to the illuminating light being broadband. So broad bandwidth is not an advantage; it's a problem, but we know how to solve it.
Mm-hmm. Okay, related to this question, so since you can only detect a couple of very limited number of modes in this case, right? So is the resolution limited by the number of modes you detected, or by what factors?
Well, ultimately, the resolution is limited by the number of photons available. It's a complex question, right? Mm-hmm. So ultimately, the resolution is still limited by the diffraction, by the bandwidth limit of the microscope objective.
Mm-hmm.
But our method allows you to better extract data for those photons that made its way through the microscope objective, and those photons that we're able to detect. Our method extracts better information from these photons, but the ultimate resolution limit is still the size of the objective lens, the numerical aperture.
Mm-hmm. Okay, so if you, for example, if you can, since the microscopic objective is kind of band limited, right? So that means we only detect kind of frequency cutted information
that's correct.
of the components, right? So if we are able to decompose the light field captured by the detector by using neural network onto different kind of modes, and I assume that this modes we detected actually also kind of band limited, which means we may lose some information about these modes, right? So is it possible, for example, by using a neural network to guess or to regenerate the whole spectrum of these modes, and in this way, is it possible to increase the resolution?
Well, it's more that direct imaging imposes additional penalty on high bandwidth photons, right? Yeah. So in the Fourier plane, the objective lens sets the limit, but the direct imaging makes it further turns out that it further attenuates higher bandwidth photons. So higher bandwidth information is not optimally detected with direct imaging. And what our method does, it detects this information better, right? So it performs a better measurement on that part of the spatial spectrum. However, we're still limited by diffraction. So essentially, well, in direct imaging, you can do deconvolution, right? So you can improve. So if you have like an infinite amount of light and no noise in detection, then you can do deconvolution and you can improve your resolution. Right? So essentially, our method is equivalent to deconvolution. The problem is that with direct imaging, you're limited by noise, by both technical noise and shot noise. So you cannot always do deconvolution. Right? So our method increases the range of situations, right? The range of brightnesses and noise levels for which this is possible.
Okay, great, thank you. Okay, so there's another question about the paper you published in Advanced Photonics. The question is, optically calculating the MVM, is there any difference between this and the diffracted neural network? Or is it possible to do the optical backpropagation for diffracted neural network?
Technically, it's the same. It is possible to do optical backpropagation. You see, diffractive neural network doesn't have activation, doesn't have an activation function.
Right.
So it's quite easy to do backpropagation through a linear part of a neural network, as we discussed. And our achievement has been to extend backpropagation to also the nonlinear part of a neural network and show that the entire neural network can be trained end to end, including activation functions.
Okay. So and also in the optical computing, whatever technology you have so far, kind of analog computing, right? So is it possible to develop kind of digital optical computing in a way? Or?
Well, that's something that's been pursued in the 80s. So optical computing technology has been pursued. There was not much success. And well, as discussed, digital computing has shortcoming due to its it has inherent shortcomings due to its nature. Right, so you have to decompose the data into bits, and then everything becomes more expensive. So actually, we want to get away from digital computation towards the analog computation, see what we can achieve with analog machine.
Okay. And and then now there's another question from the audience. Is the resolution related to the size of the object?
The resolution is limited, is determined by the numerical aperture, right? So it's the same principles for example, microscopy and astronomy, when sizes, the linear sizes are very different, but the resolution is limited by the angular size, right? So the angular resolution is lambda over d, where d is the diameter of the lens.
Yeah. Okay, there's another question from the audience. So I think the student is working on the kind of diamond color center systems. So his question is, can optical neural network be implemented in the diamond color center system for diamond-based quantum computing and quantum networks?
That I won't be able to answer because these systems are very different. So, it has to be analyzed in more detail, what specific tasks we're trying to solve and how the nitrogen vacancies can be of benefit here. It's very different systems.
Right. Okay. So are there any questions from the audience? Okay, so I have a further question about the optical training.
But last question, please.
Yeah, sure, of course, yeah. Then now the last question, I promise. So I'm wondering if so now you're able to do the optically backpropagation, right? How about the time and how much time it takes to do the backpropagation in optics?
Oh, that's the same speed of light. It doesn't take a long time. It's more like, but in practice, of course, it's more difficult to do it precisely because backpropagating light has to follow in exact footsteps.
Right, exactly. So that means you need to make the alignment, right? And also the generate the conjugate of the output, something like that.
That's right. Well, conjugation is not that difficult, right? It doesn't have to be conjugation. It can just be backpropagating light.
Okay.
But alignment is critical, and of course, with high dimension becomes more and more difficult. Right. I suspect that in an integrated setting, it might be easier.
Okay. All right. So I think we have enough questions, and I would like to thank Alex one more time for his time and his share for the wonderful paper and wonderful work published in Advanced Photonics. And I would like to invite you to publish furthermore papers in the journals. Thank you so much.
Oh, thank you very much too, and congratulations on creating this amazing journal.
All right. Thank you so much. Okay. Now. So you have a great day. OK， 好了，各位听众。